Okay, so in the last video we talked about the concept of adding vectors, and we talked about how to add vectors in kind of a qualitative, non-calculation-y way using the tip-to-tail method. And in this video we're going to talk about a different method of adding vectors, that is adding vectors by components. And this is a much more quantitative and precise type of way of adding vectors, and really the main focus of what we're doing this unit all comes down to adding vectors by components, because of course when you're doing problems with Newton's second law, what you're doing is you're adding vectors. Okay, and so the tip-to-tail method is kind of a useful tool if you need to really quickly figure out which way a resultant vector is going, but typically if you want anything more precise than that, you would have to use the component method. Okay, so here are the steps to adding vectors by components, and before I go through these steps, let me just kind of give you the big picture of how the component method works. Now we know, of course, all vectors can be thought of in terms of their components. You know, x, y, and z components. Typically at the high school level, we don't talk about z components. So as we've seen in the past units, vectors have x components and y components, and you can't just add the magnitude straight together with vectors. So basically what we're going to do is we're going to take the vectors that we want to add, whether it's 2 or 3 or 4 vectors, we're going to break them into components. Okay, that is, we're going to break them into x pieces and y pieces. We're going to add up the pieces separately, and then we're going to put everything back together again. Okay, that's basically how this works. And so if you look at the steps, step 1 says break all vectors into x and y components. Pay attention to signs. That was a big issue that we had when we did projectile motion, because a lot of people forgot to take into account the direction by worrying about the signs, whether a component is positive or negative. You add up the x components and y components separately. Remember, we have the bracket notation to write a vector using its x and y components. Now, when I say add up the x and y components separately, what I mean is you add up the x components, and that gives you the x component of the resultant vector. You add up the y components to each other, and that gives you the y component of the resultant vector. Then, once you have the x and y components of the resultant, you are going to use that to reconstruct the resultant vector in its entirety. The magnitude of the resultant can be found using the Pythagorean theorem, and the direction of the resultant, okay, remember we typically indicate direction with an angle, can be found by sketching the components of the resultant and then using the inverse tangent function. And so in situations where you're asked to find the magnitude and direction of the resultant vector, you should end up with a magnitude, which is just a number, and plus an angle and some given direction. Okay, and so I kind of outlined the general method for adding components here, and these pictures are basically just meant to visualize what I just described. I don't really think there's anything new on this slide, but if you do look at these pictures, you can kind of see this top picture kind of explains how the component method works. Let's say you want to add vector A to vector B, and A plus B is R, where R is the resultant vector. Then what you do is you find the x component of vector A, the x component of vector B, you add those two together, and that gives you Rx, and then you do the same thing with the y components. Here you have the y component of vector A, the y component of vector B, you add those two together, and that gives you Ry, which is the y component of the resultant. Then given those two things, you can find the magnitude of R using the Pythagorean theorem, like you can see there in the bottom picture. Okay, that would just be the square root of Rx squared plus Ry squared. And then you can find the direction by using the inverse tangent function. Okay, so if you see anything else new that stands out to you, please go ahead and add that to your notes. Otherwise, we're going to go ahead and jump into some calculation examples. Okay, so let's take a look at example 1, and we're going to start off with a pretty basic example here. So, it says a boat traveling north along a river at 15 meters per second must fight against a water current which is traveling at 5 meters per second east. Determine the resultant motion of the boat by sketching the two velocity vectors sketching these two velocity vectors, sketching the resultant vector using the tip-to-tail method, and then using the component method to find the magnitude and direction of the boat's resultant velocity. Okay, so there's a lot going on here, so I'm going to switch over to Notepad tab in a second. But basically, we have a vector addition situation here. The boat is traveling north, but the water in the river is going to the east. And so what's going to happen is the boat is going to get pushed at an angle. And so just to kind of diagram this out, let's see, we have 15 meters per second north and 5 meters per second east. And so if I sketch this out, let's see, say 15 meters per second north. And let's say the river is going 5 meters per second east. I don't know why I'm doing that. 5 meters per second east. And of course, what's going to happen, let me move this 15, actually, it's kind of in the way now. What's going to happen is that the boat's trying to head north and the water is going to the east. The boat is actually going to move to the northeast. Okay, and so the resultant vector would be something like this. And so I'm going to call this VR, where V here is the velocity and R means resultant. And so the boat, even though it's trying to head north, is actually going to get pushed so that it heads northeast. Okay, so step 1 is to write each of these vectors in terms of their x and y components. Now, just to be able to label this, I'm going to call this vector over here, I'm going to call that R river. And this 15 meters per second, I'm going to call that V river. And this is going to be V boat. Okay, now, V river, it tells you in the problem that it's moving 5 meters per second to the east. And so let's assume a coordinate system whereby, north is a positive y direction and east is the positive x direction. That means the velocity of the river should have an x component of 5 meters per second and a y component of 0. And likewise, V boat, that's trying to head north, is going to have an x component of 0. And again, the reason is if you look at this vector pointing to the north, no part of that vector is going in the x direction. Remember, when we talk about components, that's what we're really talking about, is how much of the vector is pointing in the x direction and how much of the vector is pointing in the y direction. So if it's pointing completely in the y direction, that means it has an x component of 0. And it has a y component of 15 meters per second. Okay, and I basically want to find VR, or V resultant, which is the sum of these two vectors. Okay, now, I've already sketched these two vectors, and I've sketched the resultant using the tip-to-tail method. That's basically what I did right here. Notice when I drew this out, I kind of implicitly did the tip-to-tail method. I did vector 1. I put vector 2 with its tail starting at the tip of vector 1. And then the resultant starts at the tail of the first vector and goes to the tip of the second. And so when I drew this up here, I kind of implicitly, subconsciously did the tip-to-tail method without intending to. But now I want to do the component method. And so I already have the x and y components of these two vectors. And so I'm going to add the x components together. So I'm going to do 5 plus 0, which is 5. And then I'm going to add the y components together. I'm going to get 0 plus 15, which is 15. And that means my resultant vector has an x component of 5 meters per second and a y component of 15 meters per second. Now that does not answer the question, because the question asked me to find the magnitude and direction of the resultant. Now I have the pieces of the resultant, but now I need to put them together. Okay, and so just to clarify, what you would normally do at this point is you would sketch out Rx and Ry. So here is, and when I say Rx and Ry, I'm just talking about the x and y components of the resultant. So I know that the resultant has an x component of 5 meters per second. And I know that it has a y component of, I don't know why I'm drawing it over here. I know it has a y component of 15 meters per second. So if I want to find the magnitude of VR, that would be right here. I can do that using the Pythagorean theorem. So the magnitude of the resultant velocity would be the square root of 5 squared plus 15 squared. And then I'm going to square root that. Okay, so 5 squared plus 15 squared square root is about 15.8 meters per second. So the magnitude of the resultant velocity is 15.8 meters per second. Which is interesting because notice that even though the boat itself can only travel 15 meters per second, it's actually sped up a little bit by the river, which is interesting. Now I'm not done with the problem because I also need the direction. Remember, direction is typically indicated with an angle. So let's say this angle right here. Now this angle right here would of course be the east of north angle. I also could have drawn this completely differently. I also could have drawn it so that the x component was down here and the y component is up here, and then I would be talking about this angle, which is the north of east angle. Now honestly it doesn't matter which one you do because they're both equivalent to each other. As long as you show your work and as long as your work is correct, then you'll get full credit. Okay, so what I'm saying is there's two possible answers to the direction. Okay, because the two angles are complementary to each other. So let me explain what that means. So let's find this top angle up here. What I would do is I would say theta equals the inverse tangent. I'm using tangent because the 5 is opposite to this angle and the 15 is adjacent to this angle. I'm using inverse tangent because I want to find what angle that is. So the inverse tangent of 5 over 15, and I'm going to type that into my calculator, and I get 18.4 degrees. Now that angle, though, is the east of north angle. So the answer to the question could be 15.8 meters per second at 18.4 degrees east of north. Sorry, this is the east of north angle. Now, what if I had done inverse tangent of 15 over 5? In other words, what if I had gone with this bottom picture right here? Because for this angle down here, it's flipped. Because for this bottom angle, the opposite side is 15, the adjacent side is 5, and so I also could have found that complementary angle by doing the inverse tangent of 15 over 5. And if you do that, just putting it into my calculator, you get, just going to round this, by the way, you get 71.6 degrees. But if you look at 18.4 and 71.6, you should hopefully notice that those two angles are complementary to each other, in the sense that they add to be 90 degrees. So I could say 15.8 meters per second at 18.4 degrees east of north, or I also could have said 71.6 degrees north of east, and either of those answers would have been fine. Okay, as long as it's correct, it's correct. But notice here, this is the magnitude, and either one of these two things is okay for direction. Okay, but you have to have the angle, and you also have to have the coronal along with it. Because 18.4 degrees, there's lots of 18.4 degrees out there, so you need to specify it's 18.4 degrees east of north. Okay, so pause there if you want to look at that. Again, that is example 1. Okay, so moving on. Let's take a look at another example. So example 1.5 says, add the following vectors and find the magnitude and direction of the resultant. Assume that the x-coordinate system is east-west and the y-coordinate system is north-south, which we usually do anyway. Now in this case, I've really kind of tried to simplify this example. Typically when you're doing these calculation problems, one of the things that takes the longest is actually calculating the x and y components of each vector. In this case, I've actually given you the x and y components of all of the vectors. Okay, and I'm basically just asking you to find the resultant. Alright, so given the components, find the resultant using the component method. I'm going to call it R, just kind of generically for resultant. Finding the components of the resultant is super easy, because all I'm going to do is I'm going to add up the X components, I'm going to add up the Y components, and then I'm going to reconstruct my entire resultant vector using those things. Okay, so the X component of the resultant I would find by doing 14 plus -2 plus -7, and that would give me 5. And then I'm going to add up the Y components. -12 plus 2 plus 2 is -8. Notice there's no units here. I'm just kind of talking really generically about vectors. Remember, vector math is something you would normally learn in pre-cal or IB math, except I think they took it out of the IB curriculum. And so you can do these types of vector problems without worrying about what the units are. The process is the same whether you're adding velocity vectors or force vectors. So in this case, we don't have any units on anything because we're just kind of talking about generic vectors. Okay, so what I have here is I have the X and Y components of the resultant vector. Now, what does this mean? Well, it means if I think of my resultant vector, I know that the X component of my resultant is pointing in the positive X direction. And I also know that the Y component of my vector is pointing in the negative Y direction with slightly more magnitude. Okay, something like this. So this is Rx, this is Ry, and so if I want to reconstruct the entire resultant vector, that is R, that would be this way. I don't know what I was doing there. I tried to do a dotted line and then it didn't work. Okay, so the resultant would be like that. So this is R. So if I want to find the magnitude of R, I can do that using the Pythagorean theorem. That would just be the square root of 5 squared plus -8 squared. Okay, so I'm going to do that in my calculator. And I get 9.4 for my magnitude. And then the direction, it depends on how you draw the picture, of course, but based off of the way I drew my resultant, the direction I can indicate using this angle here. So this angle right here, I can find using inverse tangent of Ry over Rx, that is 8 over 5. You might ask, why am I not doing, sorry, this is theta, by the way. You might ask, why am I not doing the inverse tangent of -8 over 5? The reason for that is because sometimes the calculator can give you wrong answers if you put negative signs in for inverse tangent. And honestly, you don't really need the negative sign because the negative sign does nothing for you. What the negative sign indicates is direction. But you don't need help with the direction because if you draw out the picture like this, then you can see what the direction is supposed to be. I can tell by looking at the picture that this is going to be the south of east angle. And so I don't need that negative sign in front of the 8 to help me with anything. So in other words, that negative sign in front of the 8 does nothing for me. In fact, it might even give me the wrong answer. And so when I go to calculate the angle, I'm going to leave out any signs, and I'm going to take care of the direction part on my own. Okay, that's why I'm doing inverse tangent of 8 over 5 and not -8 over 5. Okay, because inverse tangent of 8 over 5 is about 58 degrees. And I know that 58 degrees, based on the picture I drew, is 58 degrees south of east. Okay, if I did inverse tangent of -8 divided by 5, then I would get -58 degrees. And then people would be asking me what that means, and why is the angle negative, and all that stuff. And I would just end up explaining things that are not really important. Okay, because again, what does that negative angle get me when I already know that the direction is south of east? Okay, so the answer to this question, if I want to find the magnitude that's 9.4, the direction is 58 degrees south of east. Okay, so those are the two answers to my question. Okay, so pause there if you need to look at that some more. Before I go on past example 1.5, I just want to point out one more thing. Sometimes people, especially if they don't fully understand the concepts behind vector addition, will tend to make really serious mistakes when they're sketching this out. For example, I have seen many people over the years do something like this. They find Rx and they find Ry just fine. And then what they'll do is they'll say, okay, this is Rx, this is Ry, and then this is the resultant. And that just doesn't make any sense at all. And what they're doing here is they're, number one, they're not correctly applying the tip-to-tail method to add Rx and Ry to each other. And number two, they're not understanding the concepts involved behind components. Okay, because look at what I ended up with. I ended up with something pointing in the negative x direction. Alright, but if you look at Rx is pointing in the positive x direction. Okay, that doesn't make any sense. If you have a vector to the right and a vector going down, your resultant should be going to the right and down, not like diagonal down and to the left. That doesn't make any sense. Okay, so what the resultant should actually look like in this case is it should actually be more like this, as we just saw. And so just think about what it is you're doing and make sure that you're reconstructing your vector correctly. Okay, so let's go on to example 2. And as far as vector component problems go, this problem is probably about as difficult as you could expect to see, because in this problem we have to do basically everything. Okay, so it says Mr. Walker walks 25 meters at 30 degrees north of east. He then turns and walks 15 meters at 45 degrees west of north. And then we're asked some questions. Okay, so this is going to take up some room. And so before I move over to Notepad, I'm just going to identify my givens. Let's call this whole vector, these are obviously displacement vectors based off of the units that were given meters. So I'm going to call this first vector S1, and I'm going to call the second vector S2, just to have something to call them. Okay, and so basically my goal is to find the components and the magnitude of the resultant vector. I don't know why it doesn't ask for the direction, because we could also find that, but that's fine. Less work for us. Okay, so let's do this. 25 degrees, or 25 meters, 30 degrees north of east. So S1 is 25 meters at 30 degrees north of east, and S2 is 15 meters, 45 degrees west of north. At 45 degrees west of north. Okay, so if you go back and look at your steps for adding vectors within the component method, step 1 says to find the components of the vectors that you want to add. So in this case, I need to find the x and y components of S1 and S2. Okay, so I'm going to try to do this relatively quickly. This is something that we've done this before, and so it should be somewhat familiar, but it has been a while. So I'm just going to kind of do this over here, and you can see what it is I'm doing and hopefully follow along. 25 meters, 30 degrees north of east, that angle is down here. So S1x, let me do this in a different color. So S1x would be this part of the vector, and S1y would be this part of the vector. So this is S1y, this is S1x. And from doing many problems like this before, we know that S1x is going to be 25 times cosine of 30 degrees. And S1y is going to be 25 sine of 30 degrees. And so that's going to be 12.5 meters there. And then the x component is going to be, let's see, 25 cosine 30 is 21. I'm going to round it up to 21.7 meters. And both of those are positive, by the way. Okay, so I have the components of S1. Ta-da! I know that S1, I would write that in vector component notation as 21.7, comma, 12.5 meters. If this was a test question, by the way, the entire question would probably be like 9 points or something. What we just did just now, that's probably like, I don't know, 1 point. Okay, finding the x and y components of a vector at this point should be a very, very easy thing for you. Okay, so I'm going to do it for S2 now. I'm going to erase this, so pause it here if you need to look at that some more. Okay, so for S2, the vector is 15 meters at 45 degrees west of north, so I'm going to sketch that out. So this is S2. So this is west. This is north. West of north would be this angle here, so that's 45 degrees, and the magnitude was 15 meters. And here is my x component that's pointing to the west. Here is my y component that's pointing to the north. So this would be S2y. This would be S2x. And again, we've done this type of problem before. This is something that you should be comfortable with because we did it a lot in the projectile motion unit. S2x would be 15 times sine 45 degrees. You'd be using sine because the x component is opposite to this 45-degree angle. And because it's pointing to the west, there would also be a negative sign out there. Okay, so 15 times sine 45 would be 10.6, and so that would be negative 10.6 meters. And S2y would be 15 cosine 45 degrees, which coincidentally comes out to be the exact same value, 10.6 meters. It comes out to be the same value because sine of 45 and cosine of 45 are the same number. And so that means I can write S2 in terms of vector components. That would be, let's see, negative 10.6, comma 10.6 meters. And now given this, I can find S1 plus S2, which I guess I will call SR for the resultant displacement. Okay, so now we get to the new stuff. Everything up to here was just stuff we've done before. Now I'm going to be adding the x components up. So 21.7 plus negative, don't forget the negative sign, negative 10.6. So 21.7 minus 10.6 is 11.1. And then I'm adding up the y components. I get 12.5 plus 10.6, which is 23.1. One of the benefits of the component method, by the way, is that you can use the component method no matter how many vectors that you have to add. And so if I had to add like 10 vectors, I would do the exact same process. It would be a pain to do. And practically speaking, you'd probably never have to do more than like 3 in a problem because it kind of gets to be a pain to do. But the process allows you to add however many vectors you want, as long as you have them in vector component form. So now that I have, the components of my resultant vector, I'm ready to reconstruct my resultant vector and find the magnitude. And I don't think I was asked to find the direction, but I could also find that if I wanted to. Okay, so from here, the next thing we want to do is we want to make sure that we sketch the components of the resultant correctly. What do I know about SR? Well, I know it has a positive x component. It's 11.1. And I also know it has a positive y component. I don't know why I decided to draw it like that. It has a positive y component of 23.1. And so the overall resultant, SR, is going to be here. And I'm not going to find the direction just, to save a little bit on time, but I could find that angle if I wanted to. The magnitude I can now very easily find using the Pythagorean theorem. That would be the square root of 11.1 squared plus 23.1 squared. And then the direction I could, of course, find using, inverse tangent. Okay, so I'm just going to type this into my calculator, 11.1 squared plus 23.1 squared, square root, and I get the magnitude of the resultant is 25.6 meters. So in other words, I go on this walk, I walk 25 meters in one direction, 15 meters in another direction. Overall, I'm 25.6 meters from where I started. Okay, so just because I walked a total distance of 40 meters doesn't mean that my displacement is 40 meters. So if you want to understand in this context, what are we doing physically? Like, what is the meaning of what we're doing? In this case, if you think like back to the beginning, distance versus displacement, my distance traveled is 40 meters, because 25 plus 15 is 40. But the displacement, how far I am from where I started, is 25.6 meters, because I did a little bit of backtracking, because I walked north of east and then I walked west of north. And so I'm not as far from where I started as you might think. Okay, so, and if I want to, I could go on and find the direction of that with the angle as well. Anyway, that is adding vectors using the component method. You will absolutely see problems like that again, and that is going to be a big chunk of points on your next test. Now, most of this unit is about Newton's second law, and so it's going to be a big chunk of points. It's not going to be like half the test or anything, but it could easily be like 20 or 25% of the points on the next test. And so do keep that in mind. As always, please let me know if you have any questions, and I'll see you guys in the next video.